So this is the last lesson of the chapter, right? We'll have a quiz. Next class will come. We'll go over the homework. We'll go over the quiz, and have a study guide to get ready for the test. This is pretty much identical to the lesson you should have gotten in Algebra 2 Trig if you were in that class. There's nothing really that much different about it. We're going to learn about inverse functions. So first thing to understand of an inverse function. Okay, we're going to be using this notation. If a function is f of x, the inverse has got a little superscript of -1. That means the inverse function of x. An inverse function does exactly the opposite of what the function does. For example, if the function value f of 1 equals 3, then f inverse of 3 equals 1. They point in opposite directions. Okay, Matt. Okay. Here's an example of pretty basic inverse functions, right? F of x is x plus 4, okay? F inverse of x is x minus 4. Okay, so here's just for some values of x, some ordered pairs. Not by all means all, right? Because you could plug anything in for x. But if you plug in x equals 1 into the function, then f of x equals 5. Add 4, right? F of 2 equals 6, f of 3 is 7, f of 4 is 8. For the inverse, it's exactly the flip. X and y are interchanged, right? Because now we're subtracting 4. F inverse of 5 is 1, right? F inverse of 6 is 2. These are exactly a switch of the x's and the y's. That's what you expect an inverse to do, to take you exactly the reverse direction of what the function is. Right? Here's their graphic right here, which is actually very important, very important. If our function has a domain and then the arrow is pointing from x values in the domain to f of x values in the range, then for the inverse is exactly the reverse. The inverse is taking values that are in the range of the function and pointing backwards into the domain. So in a sense, the range of f is the domain of the inverse. The domain of f is the range of the inverse. Right? They are exactly each other's domain and range. And we have to use that fact. I'd say that by the end of the lesson, that's like the most important detail that to solve the hardest problems is that one thing. Right? The domain of a function is the range of the inverse, and vice versa. Okay. Ken's done. Madison, you good? Okay. And this is just you don't have to copy this down, but just think of it like this. Let's say you had a job that paid $10 an hour. If I want to define a function which tells me how much you're going to get paid for the week, what do I need to know? How many hours did you work, right? So let's say you worked 20 hours. How much are you going to get paid? $200, right? That's the function. The inverse function would be tell me how much you got paid, and I'll tell you the hours you worked, right? What if you made $300 that week? How many hours did you work? You worked 30, right? That's what the function and its inverse do. Okay. Now here's what we know about functions and their inverses. And that's why we have to learn these things in order, right? We do the composition of functions, and then the next lesson we do the inverses. Because the composition of a function and its inverse, whether you do it in the order of f of f minus 1 or f minus 1 of f, they always cancel each other out if they are functions. Right? So if you're not sure if two functions are inverses, take the composition and see if the result is x, literally just x. Everything else ought to be canceled. You're just going to have x. You all right there, Allie? Okay. So here's always the first few problems they're not crazy about, but maybe they make a point. If the function is 1/5 of x, what do you think the inverse should be? 5x, right? It has to do exactly the opposite of what this did. So the inverse is and when they're that easy, like the x plus 4, x minus 4, you could probably just guess them and figure them out. They won't always be. Okay, now that we guessed the inverse, let's verify. Let's take the composition. F of f minus 1 of x equals f of f minus 1 of x. Okay, which we know that means replace the f minus 1, the inner function, with what it equals, 5x. And then evaluate the outer function, meaning plug that 5x in for the x here. 1/5 times 5x equals x. Cancel each other out. And then it has to work both ways, right? It can't just be you check f of f minus 1, you got to check the f minus 1 of f. Reverse the order. F minus 1 of f of x equals f minus 1 of f of x. Okay, then replace the f of x, the inner function, with what it equals, f minus 1 of 1/5 x. And then evaluate the outer function. Plug this in there. 5 times 1/5 times x. That's what you expect for the function and its inverse. Everything else cancels, and all you have is the variable x that's left. Good? Okay. All right. And actually, we already did that. So the next is, which one of these two, what do we expect is going to be the inverse of this f of x? Meaning, when we plug in this expression in the place of x there, which one of them, everything's going to cancel, and we're just going to get x. Let's do them one at a time. First, I'll put the 7x plus 4, 7x plus 4 in the place of that x, minus 4 over 7. So the 4's cancel, and then the 7's cancel, and you just get x. So that works. Right? Now, do we have to check the other? Yeah, you should check the other, but let's check. We are actually, all we have to choose is one or the other. Let's see whether this one even passes that test. If it doesn't, there's no point to having to do the reverse. Let's try put this 7 over x minus 4 in there in the place of x over 7. Okay, now is this going to simplify? I would have to find a common denominator in the numerator, right? So that'll be, multiply this by x minus 4 over x minus 4. Right, and now I've got 7 minus 4 times x minus 4 over x minus 4 over 7. This is going to be negative 4 times negative 4 is 16. 23 minus 4x. Does this thing look like it's going to simplify down to x? No, this does not equal x. So the inverse function has to be that one. And if you want, you could go the other way with it, right? You could put this in the place of that x. What would happen right away? 7 cancels with the 7, and then you'd have x minus 4 plus 4, and it simplifies. Okay, graphs of inverse functions. Okay, we're being given here 2 functions and being told that they're inverses. So we don't have to check it out. We just want to see, what does it look like when you graph a function and its inverse? Here's our function, 2x minus 3. Okay. Notice that these points, all these points, 3, 3, 2, 1, 1, negative 1, 0, negative 3, negative 1, negative 5 are all on the graph of the function, right? What we know about inverses is that means if you flip the x's and the y's, then all of those points ought to be on the graph of the inverse. And they are, right? So we have, here's the flip of this one is negative 5, negative 1. This one, it becomes negative 3, 0, negative 1, 1, 1, 2. Okay. And why have they drawn this line through the middle? Because a function, the graph of a function and its inverse ought to be symmetric with respect to this line. This line is the line y equals x. And actually, I can do this kind of, if you don't see it like that, maybe you see it like this. Here. Where am I at? I mean, that line right there ought to be a line of symmetry, like geometry terms. Meaning whatever is on the left has got a mirror image on the right. And it looks like it does. And it should, because they're inverses. And that's what we know about the graphs of a function and its inverse. They are symmetric with respect to that line y equals x. So the graphs of a function and its inverse are symmetric with respect to the line y equals x. That's the main takeaway about graphs. But it is going to copy something. I may not copy that. Okay. All right, Reva. Okay, Andy. Okay. It's going pretty fast. Okay, now, every function doesn't have an inverse. Okay? And take, for example, f of x equals x squared. Right? If I make a table of values for f of x equals x squared, I'm gonna plug in the points x equals negative 2, negative 1, 0, 1, and 2, actually all the way to 3. Now, if I flip those points, so negative 2, 4 becomes 4, negative 2, and so on down the line, what you find is it doesn't pass that first test. It must be the case that, for example, if I say f of 2 equals 4, f of 2 equals 4, then it must be the case that f minus 1 of 4 equals 2. Now, is that necessarily the case? I mean, look at right here. We've got 2 points that have x equals 4 for a coordinate. And in one of them, y equals -2. In the other one, it equals +2. But it doesn't necessarily equal +2. It's actually going to be plus or minus. So f of x equals x squared does not have an inverse. Not unless you restrict its domain. No, I shouldn't say that. I should say no inverse. Okay. So a function that has an inverse must have one y value for each x value, meaning it's a function, right? That's our definition of a function. But it also has to have just one x value for each y value. That's where the x squared fell down. Okay, when it has both of those, right? One y value for each x value, one x value for each y value, that's called 1-to-1. And when it has that property of being 1-to-1, then it has an inverse. We all good? Morgan? So in order to check to see if a function is 1-to-1, you do what's called horizontal line test. I mean, it's not a function if it doesn't pass a vertical line test. So it goes without saying that these are functions and they pass a vertical line test. For them to have inverses, for them to be 1-to-1, they have to pass a horizontal line test too, meaning a horizontal line should not intersect the graph in more than one place. So here was the f of x. Here's a quadratic, not exactly x squared, but pretty close, x squared minus 1. You know, can you imagine a horizontal line crossing in more than one place? Yes, like they've drawn it right there. So this one is not 1-to-1, doesn't have an inverse. Okay, this is an x to the third, a cubic, okay, and passes the vertical line test. Does it look like it passes a horizontal line test? Yeah, so that one's 1-to-1, that one will have an inverse. And honestly, you know, in the last edition of the book, it was a little more complicated. They presented it in a little more complicated way. They gave us 3 ways to know whether or not a function had an inverse or was 1-to-1. One of them was this, which is everybody's preferred way of doing it. Another one was to say, if a function is 1-to-1, then it's always increasing or it's always decreasing over its domain. So like this graph here is always increasing, therefore it's 1-to-1. This one here is decreasing and then it's increasing, so it's not 1-to-1. And then there was an algebraic way, which nobody liked and didn't do very well anyways, and they don't even present it here that I can find. But that would have been to say, you assume that there are two function values that are the same. F of A equals F of B. And then you prove that that means that A equals B. Meaning that actually those are two, that is the same point. It's not two different points with the same function value. It's actually the same point. So they don't even ask us to do that anymore. Now, I don't think that, I'm gonna say this, it may end up duplicating something I'm about to say, but remember what we say, that the function has to be always increasing or always decreasing over its domain. There is a way for this to have an inverse, and that is limit its domain. Then don't look at both halves of it. Just look at one part, a part that's always increasing or a part that's always decreasing, and that is what we're going to end up doing. Right? That's why we spend so much time on domain all the time, right? It comes up for everything. So if I look at just, let's say to the right, just this piece of it, then that would be one-to-one. When we get into trigonometry, inverse trig functions, that's exactly what we have to do in order for our trig functions to have inverses. And we know they do have inverses because look at your calculator. What do you see right above sine, cosine, and tangent? Sine inverse, cosine inverse, and tan inverse. But they're having to do this thing in order to make that work. Okay. So use the graph of f to determine whether the function has an inverse. You could put it in the calculator if you need to. They're giving us some pretty basic graphs here, right? So you could actually, if you could just sketch the graph. This is linear. If you write it like this, 1/2 x minus, that's minus 1/2 x plus 3/2. Right, that's mx plus b. That would have a y-intercept of 3/2. It would have a slope of negative 1/2. Down 1, right 2. So about right like that. So if that's the graph, is it one-to-one? Yeah. Sure. In fact, when it comes to linear functions, there's only one linear function that is not one-to-one. And which one is that? A horizontal line, right? A horizontal line would not pass a horizontal line test, right? But any other linear function, it will. So if you see the problem and it's linear, as long as it's not a constant, which is horizontal line, then you know it's one-to-one. You really don't need to look at the graph. You know linear functions are. What's the shape of absolute value again? It's a V, right? If I look at the V, just the most basic V, does that pass a horizontal line test? No, it's not one-to-one. How could we make it pass a horizontal line test? Limit the domain so that you only have an increasing part or a decreasing part. So this one was yes, right? And this one was no. Okay, so once you know that it has an inverse, then this is how you find the inverse. And if you look in the book, they actually give you 5 steps, of which these are 2, 3, and 4. I renumbered them. Okay, their number 1 step would have been verify that it has an inverse. Okay, and that part, and let's just assume we've already passed that step, and we're to the point of how do you find an inverse. First, if the equation starts with f of x equals something, replace the f of x with a y. It may already say y equals, so you don't have to do that step. But if it starts with f of x equals, make it y equals. We're going to do it on the next slide with these instructions next to it, and you'll see. Okay, then, just like we did with the points, switch the x's and the y's, right? Now, when you do that, it's no longer solved for y. It's solved for x. You need to solve it for y. So switch the x and the y, solve for y. And then replace the y with f minus 1 of x. And their 5th step, which I didn't include, was verify their inverses by doing f of f minus 1 and f minus 1 of f. This is how you find it. Sound familiar? A little bit. Janai, you good? Morgan, okay. Okay, last example. Find an inverse. And here's the steps again. Right, 1, 2, and 3. So here's the function that we're starting with. First step would tell me to replace the f of x with a y. Okay, then what? Switch the x and the y. X equals 2y minus 3. Then what? Solve for y. Okay, it's a radical equation. The radical is isolated. Next step would be to undo the radical by square both sides, right? So this becomes squared and squared. So this, now we've got 2y minus 3, I switch sides, equals x squared. Add 3, divide by 2, right? 2y equals x squared plus 3. Y equals x squared plus 3 over 2. And last step, change the y to f minus 1 of x. So here's our f minus 1 of x. X squared plus 3 over 2. Okay, well, what kind of function is x squared plus 3 over 2? Come on. It's a parabola, right? Would a parabola pass a horizontal line test? No, it would not pass a horizontal line test. Okay, that's where you got to go back to the original function right here and look at the domain and the range. Because remember, the domain and range of the inverse is going to be the swap of the domain and range with the original function. Okay, what's the domain of f of x, or how will we find it? You guys got to get good at this. All right, it's not that hard. In order to make sure we're taking the square root of a positive number or 0, you take the 2x minus 3 and you set it greater than or equal to 0. Come on, it's not rocket surgery, as they say, right? Greater than or equal to 0. 2x greater than or equal to 3, x is greater than or equal to 3 halves. Right? That's the domain of this thing. Right? What is the range? What are the possible f of x or y values? What do you know about the output of a square root? It's positive, right? You assume, remember, this is not the same thing as when you're solving an equation, you have to put in the plus or minus. When you see a square root in your equation, you assume it's positive. It's the principal positive square root. So we would know that the range of our f of x is y greater than or equal to 0. All right, that tells us, yeah.
So does an undefined outcome mean that there's no points there, like the line doesn't pass to the point?
Yeah, it's not going to go to that point. You mean like what happens if that's negative?
Yeah, so
it won't be in our graph. The graph won't go there. You'll see. Okay, now, the domain and range of the inverse, we know that the domain of f minus 1, right, has to be the range of this, except just switch x for y. This will be x greater than or equal to 0. And what will be the range of the inverse? Yeah, y greater than or equal to 3 halves. Range, y greater than or equal to 3 halves. Okay, let's look at our graph then. should have thought more about that. Let's see, where are we at? We'll do it on the calculator. Okay, so let me put this in the calculator. 2xy equals the square root of 2x minus 3. Second, square root 2x minus 3. Graph. Okay, you see the big graph right there. It's pretty much what we would expect it to look like. It's a radical. It's been shifted to the right because of that. Okay. Now, we're going to put in the inverse, and that is that function right there, x squared plus 3 over 2. But remember, now I got to limit the domain. The domain is going to be x is greater than or equal to 0. So I'm going to do that using the parentheses and all that. So on this second line, go down, parentheses, x squared plus 3, x squared plus 3, that didn't go, plus 3, and that's not good. I need another set of parentheses. Right, x squared plus 3. That's in parentheses, divided by 2, in parentheses, divided by, now I got to put the domain. It's x greater than or equal to 0. So x, second math, greater than or equal to, it's 4, and it's 0. Now I hit graph. And you see, it's limiting it. The domain is starting here and going to the right. The range, you know, what did we say for the range? Greater than or equal to 3/2? That looks about right. Right, that looks like it's starting at about y equals 3/2. Now, if you want, you could make it look, everything look a little more symmetric by making, instead of zoom normal or zoom standard, make it zoom square. Right, then everything's the same in each direction. That's zoom 5. And if you really want to see it, then maybe you go back to y equals and put in the line y equals x. Show how it looks like it's a line of symmetry. In fact, I'm going to make that a different kind of line. Not that. Not that. How about that? So does it look like these are mirror images with that being the line of symmetry? Yes. But again, if we would not have taken into account domains and ranges, this graph here would have been a whole parabola that wouldn't have passed the horizontal line test. Right? The only reason this works is because we're limiting the domain and range according to the original function. So that's the last part of this that you just have to be careful about, that one part, domains and ranges. Clear as mud, as they say? Okay. That's what we did. That is the homework. Remember, it's odds. All of them are odds. You want to write that down, and then we're going to take a quiz.